This video is going to be an example of how you can use kinematic graphs to solve 1D problems. So there's a speed skater that's moving across frictionless ice in this problem. We're given the initial velocity, and then she hits like a certain distance where the ice is rougher that's going to cause her to slow down. We're also given the final velocity. So let's make a listing of what's known in the problem. We're asked to find the acceleration that is producing the slowdown, the exact numerical value, and also the amount of time that was spent on the ice. So just organizing the information here. Like this. Okay, so the first objective here is going to be to draw a kinematic graph. Usually I like to start with a velocity because it has the most information in it. So if we were to try to draw a graph of velocity, then a full graph might look something like this. We know that she starts out moving at a certain velocity, and before she hits the rough patch, velocity is basically constant. Once the rough patch is encountered, then the velocity is going to slow down. So we're going to have some decline in velocity there. And then eventually she's going to hit the final velocity down to this lower value, the 5.5. And then after she leaves the rough patch, then she'll continue constant again. So this graph would represent kind of a more complete view of how the motion looks. However, we should probably notice that everything important in this problem is just occurring right in this middle section where the slowdown occurs. We'll not ask anything about what happened before or anything that happened after. So what I really maybe prefer to do is see if we can try to just focus in on only that section of the graph, just to make things a little bit less cluttered. So just on that one section where the slowdown occurs, we know that we start at this initial velocity here. We decline based on the rough patch of ice to a lower value. This is going to be the final velocity here. And so translating the description of the problem into a graph, the velocity should just be a slope, a straight slope down in this kind of a way. On the time axis over here, I call this unknown amount of time delta t. Furthermore, the distance between the initial and the final is known to be delta v. This distance here would be vf, and so on. Furthermore, we can identify that the area underneath the curve is going to represent the distance. Area underneath the curve on a velocity graph represents distance. So everything under here is going to be the delta x, and that would include the full amount of area underneath the curve here. Also helpful is going to be to draw an acceleration graph of what happened during this time. And on the acceleration graph, we're going to have a constant negative acceleration during this entire time because we know that there's a consistent slowdown while we're on the rough patch of ice. So we'll get a nice rectangle here. Delta t is the amount of time that it takes for the slowdown to occur, and then this is the acceleration that's unknown, a. The area inside of or under the curve on an acceleration graph represents the change in velocity. So all the area kind of in this region is going to be delta v. And we recognize that delta v also is over here on the velocity graph. It would be on the velocity axis, that vertical distance there. So once we have our graphs drawn out, then the objective is just to use simple geometry on the graphs to try to write equations out. So what that's going to look like here would be the area delta x being equal to the combination of the triangle and the rectangle that you see there. The triangle on top is going to be 1/2 base, which is delta t, times height, which is delta v. And then we'll be adding the area of the rectangle, which is base delta t times height, which is vf. So this is an equation which represents a relationship between the position and velocity and other quantities on that graph. For the acceleration graph, the area delta v is going to equal the base delta t times the height a. So these two equations are both going to be helpful for trying to solve for what we want to figure out. I'm going to go with the first equation first because I recognize here that there's only one unknown in that equation. That would be delta t. The second equation, delta t and a are both unknowns. That equation is going to be harder to work with, and so we'll start with the first equation. If we work to try to simplify that equation, now we just need to do a little bit of algebra. So I'm going to factor out the delta t so we can get delta t appearing in only one location, and then we'll just divide that multiplicative factor to the other side to try to solve for delta t. All of these now are knowns. The delta v looks like it's going to be 3 meters per second if we subtract the vi and the vf from each other. And then delta x is the 5.3 meters. When we plug in the numbers here, we get 0.757 seconds. Now that delta t is known, it's going to be easier to go back to the velocity equation, and we can plug in what we know over there. So based on this equation, a is going to be equal to delta v over delta t. Delta t is now known. Delta v was already known. We can plug in numbers here and find that the acceleration is going to be 3.96 meters per second squared. I'm going to prefer to put a negative sign on that acceleration because I know that the acceleration is slowing the velocity down, and so rightly I should have a negative sign on that. So with this, this basically completes the problem and gives us the acceleration and time that this process took to occur.